Ladies and gentlemen, good morning. My name is Zhisheng Niu from Tsinghua University, Beijing, China. Today, I'd like to share with you some of my thoughts on 6G and provide a new horizon for energy-efficient design of 6G networks. Here by 6G, I simply means the mobile communications networks in around 2030, without any specific definition on any particular technologies. If we have to say something on it, I think it could be called mobile things or mobile society, embedded with more intelligence, rather than just a mobile phone in first generation and second generation, and the mobile internet in third generation and fourth generation. For this purpose, future 6G networks have to include more computing facilities to execute big data analytics, which may in fact consume much more energy than base stations. For example, a simple high-performance CPU and GPU may consume as much as the energy to run a 4G LTE base station, while a typical edge server may need tens of such CPU or GPU cores. On the other hand, as shown in this table, the data processing for model training or inference may cause extreme amount of CO2 emission. In addition to that, as shown in this figure, our love of the cloud is making a green energy future almost impossible. It is expected that the energy consumption of data centers in 2025 will be the top share among all the ICT sectors, almost a 10 times increase than 2015. As a result, we should not only consider the energy reduction of base stations, but also those edge servers. But as shown in this figure, the traffic demand is continuously increasing anyway. Therefore, the key question will be, can we send more information with less energy? In short, SMILE. If yes, how should we coordinate the heterogeneous base stations and also between base stations and edge servers? This is definitely not an easy task, if not impossible. To make this impossible possible, I think there are three approaches that we can take. One is energy saving by more aggressively turning off the underutilized base stations as well as edge servers to reduce the energy waste. The second approach is to incorporate more renewable energy by energy harvesting technologies. And the third approach, which is the main topic of today's talk, is to use AI on demand. In the following, I will introduce these approaches one by one. For the energy savings, the key issue when we want to turn off the underutilized base stations is how to provide the coverage guarantee. To solve this problem, we have proposed a so-called hypercellular architecture, in which the coverage for control information and the coverage for data service is decoupled, so that the coverage is always guaranteed by control base stations, while the data base stations can be switched off whenever the traffic is low. With this new architecture, the network planning as well as the network operations can be adapted to the traffic dynamics and therefore reduce the energy waste. In other words, the traffic flow and the energy flow are tangling for a harmonized adaptation. The fundamental problem are then which base station, when, and how long should sleep. We are then using queuing model to characterize the energy delay trade-off in base station sleeping control. And very surprisingly, found that the energy and the delay, in fact, is not always a trade-off. That is to say, reducing energy does not necessarily bring increased delay. Or a win-win solution is possible if the sleeping control is well designed. In addition, we also found that the optimal base station sleeping control is a two-threshold policy. That is, the work mode switching from adaptive to sleep mode or from sleep mode to active mode should be hysteretic in nature. For the second approach, that is using more renewable energy, the key challenge we need to deal with is the mismatch between energy supplies and the traffic demands. For this purpose, we have proposed a new concept called energy informatics for smart interaction between energy and information. In short, Einstein. The key idea here is to match energy flow to information flow, and vice versa, to match information flow to energy flow. For instance, if information is flowing up, we can pull more energy from battery. On the other hand, if information is flowing down, we can charge the battery. On the contrary, if today's energy is more than enough, we can cache the contents or push to users in advance, something like doing tomorrow's job today. Or if today's energy is not enough, we can just provide the basic service only, but postponing enhanced service to the future, something like doing today's job tomorrow. Or offloading to clouds, something like asking help from the others. Here, one of key challenges in energy harvesting system is how to deal with the triple dynamics in a harmonized way. That is, in addition to the dynamics in channel and the traffic demands, there also exist dynamics in energy supply. Another new challenges come from the new constraints of causality and timeliness of the available energy. As a result, considering energy efficiency only is not enough anymore. We should also try to avoid from energy outage and energy overflow. In other words, energy sustainability would be a key performance metric in energy harvesting systems. Last but definitely not the least is a new horizon that we should take into account. For sure, AI will be key enabling technologies for future 6G networks, but it will bring enormous energy consumption. The fundamental question is then, can we reduce it in a drastic way? The key idea here is AI on demand. That is to say, AI capability should be provided on demand. It is obvious that we don't need AI all the time and everywhere. In particular, we should only consider to use AI when modeling is impossible or extremely complicated. For example, when channel has nonlinear correlation, or there is unprecedented blockages. Second, when data is available enough, and most importantly, in high quality. Otherwise, AI will be useless. The third, when AI-based decision-making can be real-time. Otherwise, AI will have very limited use. And the fourth, when AI-based learning and inference is cost-effective and energy efficient. Otherwise, AI will not so helpful. In this regard, we have done some researches on network-assisted green AI for future 6G networks, including energy-efficient DNN, co-inference by splitting with pruning, mobility-enhanced vehicular edge computing and caching, and edge learning and cooperative inference with timeliness constraint. As one example, we have proposed an energy-efficient federated learning scheme where multiple heterogeneous workers with non-uniformly distributed energy supplies learn a shared machine learning model collaboratively using non-IID local data with the help of a parameter server. Simulation results have shown that data redundancy can significantly improve accuracy, but the marginal effect diminishes. In addition, dynamic scheduling policy can achieve close to optimal performance without violating the energy budget. In summary, greening 6G needs to take a holistic approach from radio access networks to computing facilities and further to AI algorithms. For sure, AI will play a key role in 6G development, but the usage of AI have to be on demand. In this regard, we believe greening AI is a new horizon for SMILE. To conclude my talk, I would expect everybody on the line to keep SMILE every day. Thank you very much for the kind attention.